Nageshwara.
Namaste, sir. Nageshwara garu.
Hello all. Good evening, everyone. I'm Mohanalila, Assistant Professor, ECE Department, V2IT. Welcome to all for today's session. Before starting the session, let me introduce Dr. Venkata ma'am, Professor, ECE Department, NIT, Warangal. Dr. Venkata ma'am has done her PhD in Electrical Engineering from Indian Institute of Technology, Delhi. She has joined in NIT Warangal in April 2008 as assistant professor, and she had held many academic academic and administrative responsibilities at NIT Warangal, and served as student branch counselor for IEEE student branch NIT Warangal, and won Darrell Chang Bronzy Award for best student activities. Prior to joining with NIT Warangal, she had also worked as a software engineer in Capricorn Global Solutions Private Limited, Hyderabad, and worked as assistant professor in Geetham University even, and full-time research associate at Indian Institute of Technology, Delhi, India. Her areas of interest includes wireless communication, signal processing for communication, optical communication, and design of real-time pressed bed for 5G using SDR. She had more than 100 papers in credit in national and international conferences and journals. She supervised 10 PhD students, and currently 5 more students are working under her towards their dissertation. She is a fellow of in Institute of Electronics and Telecommunication Engineers and India, and senior member of IEEE. She had published a book with CRC Press. Welcome, ma'am. Welcome to the session. Thank you for coming to the session and giving your valuable information to us.
Thank you, ma'am. Thank you.
I will make it cost 1 minute. Okay, madam. Now you can share the PPT.
Yes, sir. Yes. Just a minute, sir.
Yeah, do it.
So,
CR2 for ECA WhatsApp audio.
hello, Mahidar.
Yes, madam. Receivable, madam.
Yes, sir. Hello,
Yeah.
Mahidar.
You can put slideshow, madam.
No, I'm in another talk.
Oh,
I'm
okay,
in
okay.
another talk.
Okay.
I can complete after 7:30 only.
Will I be able to see the paper?
May not be possible today. Okay.
Monday.
Oh, Monday. Okay. Sir, is my screen is visible?
Yes, madam.
Okay, sir.
Make the slideshow, madam. Slideshow.
Yes, I'm showing. Let me join in another system also, so that sometime I have to use pen.
No issue, madam.
Yeah. 1 minute, sir.
Here itself whiteboard option is there, madam.
But this
Yeah,
this desktop doesn't have the pen.
Okay.
Let's see, sir.
Recording in progress.
Okay, sir. Now my audio is clear, sir?
Yes, madam.
Okay, I'll make a slideshow. Okay, sir?
Yeah, now it's okay, madam.
So 1 minute. Actually, your slide is making me to... Oh, okay, sir. So today, welcome to all the participants of this ATL workshop. So I will be presenting on Intelligent Reflecting Surfaces, IRS, what we are doing at NIT Warangal. First with an introduction to the IRS, then I'll go to the advanced topics, how it is helpful for 6G communication. Coming to the intelligent reflecting surfaces, why do we need to use in present 5G and 6G communications? The scenarios are like this. So I talk with some motivation, the fundamentals of IRS and what is the working principle of IRS, how the architecture of IRS, advantages, disadvantages, and their channel model and technical challenges. After completing this PPT, I'll go to the advanced version of the work what we have done in my laboratory. I'll show all the details. So coming to this physics of wireless signal propagation. So electromagnetic waves we know very well that travel at a speed of light and spread out in all directions. Okay, so if you look at the transmitter at one place and when the transmitter is radiating the signals, so in our omnidirectional space, we can find the receive power at a distance of d using the formula of transmit power by A into that is the area of the antenna by 4 pi d square. This is the fundamental principle of Phillips propagation formula. So suppose this A is lambda by 4. Lambda by 4, that means lambda is around 0.1 millimeter, that means at 3 gigahertz. We receive a power of minus 43 dB. If I increase to 10, that means I am measuring at a distance of 10 meters, then the power received is 63 dB, right? So that means what do we understand from this formula? So the power received is inversely proportional to the distance square measure. And as we are moving from away from the antenna, the amount of received power is reducing, right? That's the one problem in wireless communication systems. So look at the conventional base station antennas. So these conventional base station antennas, suppose the conventional base station antenna is with a fixed beam of 60 dBm gain it has, and so it has a 60 dBm gain. There is a huge abstraction from the transmitted beam. Then beyond that abstraction, there are some unlucky users are present. So they may not be able to receive the signal from the transmitted transmitter. So that means there is no benefit from even if you increase the antenna gain as well. So but the lucky users, we are using a 60 dBA gain, then lucky users are receiving more stronger signal, that is 40 times than the original stronger signal. But unlucky users are not getting even if you increase the gain of the transmit antenna. This is a base problem of wireless communication systems. So then, these base stations, suppose we are transmitting the signal using some control mechanism to improve the coverage of your communication. So look at the coverage of the communication with a fixed beam of 60 dBi gain. And there are some unlucky users. Suppose if you can extend your propagation path to up to unlucky users, we can improve the signal gain, right? So that means how do we improve the signal transmission length from the transmit antenna to your faraway places is unless you have to use some repeaters or use a new technology, because everywhere fixing a new base station and improving the power to those radiating to those areas is very cost effective nowadays. And some places where the hill areas, so we will see from one area of the hill, maybe in the down pit of the hill station, some users are available, but above the hill some users are available. If you are placing the base station above the hill, the down of the hill, maybe the other side of the hill, unlucky users are not getting any information. They are not receiving any information from the transmit antenna. So these are the main problems of conventional base station antennas. So to improve this coverage, what we do, so we have to formulate some control propagation mechanism. So what is this control propagation mechanism? So somehow we are extending this signal to a long distance, and once it hits that propagation, once it hits that place, from there, after hitting the signal, it is going beyond your unlucky users and also reaching to the unlucky users. That is a principle we have to adopt. So without using any extra additional base stations, we can use this technology to improve your signal strength. So in hilly areas or in most crowded areas where there are large buildings, from one building to another building, the signal is not reaching beyond of these huge obstructions, right? So there is a beam forming concept. We have already know about the beam forming concept. Suppose if you use a single antenna, and the single antenna is radiating power in omnidirectional fashion, and if you place another two antennas of the same signal and you are dividing it, so when these two signals are constructively, so the placement of the antenna is very much important. And if you place this antenna at those dimensions, at those distances, the signal is constructively adding at the center point. If you look at, I already plotted using a pen, right? Now extending it to the same concept of two antennas and the same signal, but with a different delays. So one antenna and to the other antenna, we place some delay. So because of the delay of between these two antennas, the constructive interference angle is going to change. Let's see, from the first one, it is going straight forward, constructive interference, but in the second diagram, it is going at an angle of 60 degrees. Okay, so that means what we understand, array gain and spatial multiplexing. So if you use two antennas, you can form a beam towards one direction. If you use four antennas with different delays, if you are adjusting according to that, so the beam dimension is increasing. And the four antennas with two signals, and we are dividing the power between the two beams, then we are seeing that one in red color, one in blue color. So this all depends on how you are placing the antenna elements and how do you want to extend your beam to a larger distance, right? So there is another example of two antennas, two signals, divide the power between the two beams. So this case 2 times signal gain, okay? So now, so this constructive interference, we would like to use it for our communication to extend the range without using multiple base stations at every time, at every place. So the first diagram, according to the Huygens-Fresnel principle, so every point of a scatter. So one scatter, infinite size surface is placed at this point. When the wave hits this scatter, so because of the surface, they are hitting, after hitting, they are coming down towards the other direction. That means this is called a constructive interference. This determines actually the direction of the signal upon scattering. So now another one, so beam forming. So this direction is determined by the geometry, and the bandwidth is proportional to the 1 by surface width. So if you look at the second diagram, suppose your infinite size surface is not possible. So we place a finite size surface. So this finite size surface is making, based on the elements placements, the beam forming is formulated at this position. So that means the base station development in 5G, there also the 5G in 5G technology, also they want to use this IRS, multiple intelligent reflecting surfaces. So the basic principle of this intelligent reflecting surface is, so V is a high antenna gain. So it has a passive antenna and it gives a constant directivity, right? So now there are 64 low gain antennas are placed in this format. 64 low gain antennas. So this is called an antenna array. So this antenna integrated, it is also integrated with radios and strong adaptive directivity, separate users in space. So if you can manage the delay between these antennas and phase control of these antenna elements, we can form different beams towards the different users. So who are placed at different locations. So that means we can form a beam for each individual user who are placed isolatedly in different directions in the space. So now, two ways to build a much larger arrays. So one way is an active array. Okay, so that means your holographic massive MIMO is another example. This also uses a large intelligent surface, reconfigurable reflect arrays, and some where semi-passive arrays. Some that means the elements are not fully powered, only the partially we gave a power. So this reflecting reconfigurable intelligent surface, and also it is a software controlled metasurface. This is also called a software controlled metasurface. What do you mean by software controlled metasurface? Because each element of the passive array is connected with a control unit, and that control unit is controlled by the user such that the beam formation towards the which direction to be placed, which angle it has to be elevated, everything is controlled by in a software panel, right? So that means these fundamentals and vision of reconfigurable intelligent surfaces, now we are moving to one best example how to make use of these arrays into our wireless communication. So let us look at from the antenna, because of wall penetration, so the user is receiving 20 dB signal power. Okay. And if you see the another place when the signal is coming through a window and it will come to an extra path, and to reach to the user, it takes a longer time. So that means when there is a reflecting smooth edge, so it is reflecting towards other direction. But if we are placing a scattering or a rough edge, so there is a possibility of the reflections are going in different directions. Now, so using this basic principle, so suppose if you are, because anyway the wave is coming inside the building through your window, and so at the edge of the window you have placed a reconfigurable intelligent surface RAS. So because of this RAS, we formulated the beam shape using the software control manner. So this beam is extended towards the intended user. That is a basic principle of RAS element in wireless communication. So we place several RAS elements inside the malls such that the signal is passing inside the mall and it is propagating. Okay. So that means these reconfigurable, what is this reconfigurable? So that means the properties can be changed and it is intelligent. Why it is intelligent? It is real time and also programmable and controllable, and it is a surface because it is a two-dimensional array of scatter. So this reconfigurable intelligent surface is the construction of this reconfigurable intelligent surface has one element. Suppose if we take one element of the reconfigurable intelligent surface RAS, there are many elements in this RAS. Let's consider only one element of this RAS, how it has to be constructed. It is as a passive patch, one patch antenna, and it is connected with a diode. It will act as a switch, and also it is connected with a programmable controller. So based on this programmable controller, so how many arrays are to be made on so that the dimension of or my array beam forming of my signal can be placed towards an intended user. So I can change the beam shape, I can change the beam direction by placing the arrangements of these RAS elements inside of this patch antenna, inside of this entire array. So one patch is connected with a switch and as well as a programmable controller unit. So using this control and by making on of the switch, so each element is made on or some of the elements are made on. According to those, how many elements are made on. So what is the beam we are intended to translate? All depends upon the mechanism what you are adapting. Okay, so that means RAS element is one of the very intelligent element, because so this intelligence is created because of your programmable controller. That means the pattern of impedance, approximate shape of another object, sub-wavelength size elements, everything. So when you are transmitting, they are all controlled by your programmable controller. So now, how large are the elements is important. So if you take the literature, when a signal arrives at a 30 degrees of angle, so one is coming into the antenna array, the patch antenna array, and the reflections, how they are going. So they become a discretized reconfiguration formula. So if you see the angle of arrival and angle of the maximum match is happening between your received signals are shown in this graph using a normalized gain. So angle versus normalized gain. As the angle towards the intended transmission is at 30 degrees. So at the 30 degrees, we are seeing the gain of your patch antenna is almost reaching to that component, and it is varying between lambda by 2 dimensions if you are placing. And for lambda by 4, we can see that the approach is also reaching the maximum point at the same point. Lambda by 8 is also almost same, right? Now, so how this RAS is different from your passive repeaters, which are used to place in those early days of your communication system. So if you look at, suppose if you have placed a passive repeater at this point, and line of sight is, and your antenna is placed on top of the hill, and it hits the passive repeater. That means the signal is reached to the passive repeater, and the repeater is intended to translate the signal towards the down of the hill. So this signal is pushed towards the down of the hill. But from the same antenna, if there is a shadowing, that means a huge hill is already there, and which is not passing your original signal that is there in the red color to the intended user because of the shadowing. Okay, so that means this passive repeater strength is going up to only one user, but it is unable to go to the next user. So the fully passive, and there is no power. Okay, and this fixed beam pattern, wide or strong, how to design such that your passive repeaters can reach to different multiple users. So in place of the passive repeater, we placed a RAS element. So this RAS element is constructed in such a way that using a programmable controller unit, that is a software defined controllable unit. The beams are divided between the sections. So both the beams, one blue beam is serving one user, and pink beam is serving to the another user. And in spite of this, the second user, in spite of he is hiding beyond a shadowing region, but still he is getting his signal from RAS element. So the strong beam, and it's going to the desired location. So this must be controlled, and also some power elements. Power is also required for this antenna, because we have to control which switch is to be on corresponding to the patch. So and the controllable unit also must be powered on. Okay, so this is almost similar to our cooperative communication, placing an RAS element at a distance location so that it is hitting the RAS element and making the direction of the signals towards the intended user. So if you remember your cooperative communication scenario, so this cooperative communication scenario is of similar kind, where there is a one source and there is another destination. The source, and so we must transmit the signal from source to the destination. So when you are transmitting the signal from the source to the destination, there is a one direct path. There is another entity which is controlling this radio element. That means we place another radio element over here in the question mark. So that system is passing the signals towards the destination. So this entity can be, maybe it is decoding and forwarding the signal, or it is amplifying and forwarding the signal. Two cases. So if it is decode and forward DF relay, we call it as DF relay. That means the regenerative system. First, what is the received signal from the source is decoded by this entity. Then it is transmitting to the destination. The another system is transparent system in the half loop duplex, where the signal is amplified by the entity, by your radio element, and then it is forwarded. Okay. So this is our old school analog repeater kind of a thing. So in full duplex system, we call this one is amplified and decode and forward. Amplify and forward and decode and forward. And in this system, in full duplex, we place a passive repeaters or an RIS element. So this is more or less similar to your cooperative communication system. Okay. So then why do we need this IRS or RIS, intelligent reflecting surface or reflecting intelligent surface? Both are same. So why we need this IRS? Because we want to see that array gain of your massive MIMO techniques at the base stations, and they are mitigating the path loss at high frequencies, but they fail to solve the blockage problem. So why blockage problem? They are fixed versions of antennas are placed. So many antennas are placed, but they are not designed such a way that my beam is going towards a particular some directions. Right? So it radiates in omnidirectional again. So when it radiates in omnidirectional, as with the distance, the power is also getting lost. So this RAS is needed in those places because in hill areas, in malls, we need to see that our signal is going inside the buildings, and also we need to see that the signal is going down to the hill, irrespective of any shadow areas are present. So this RAS is very useful and helpful to improve the performance of wireless communication. So only to adapt in wireless channel, but in MIMO, it sees the wireless channel, but it doesn't have any control on it. And also the channel is always random. So randomness in the channel is a significant performance loss in MIMO techniques. And in even millimeter wave and terahertz communications are also limited by the distance, as we know very well. Because as the frequency increases, the propagation path of your communication is going to reduce. Okay. And also it consumes the high power and also of wireless interference. So this controllable propagation. Now look at in the building. In the blue elements are placed inside the building. So wall to wall and to the down to the wall. So this improves the coverage of the building when the users are moving inside the building. So this RAS element as a whole, it controls actually the directivity of the scattered signal and the signal absorption and the change of the polarization. So these three aspects, it's making into control the whole system such that the signal is going inside the buildings and also going to the deep of the shadow areas. So this is how we are mitigating the shadow fading. So look at one radio station. There is a RAS element is placed over here. Because of this RAS, the signal is extended towards the intended user. And one more RAS, this is the RAS element. So it hits the RAS element and it is coming towards the intended user, right? So what is the system model for RAS aided communications? How to design a system model? We know the fundamental principles of signals and systems. When a signal is passed through a LTA system, which is having an impulse response of H, the output is the convolution between the input and the impulse response of the system, right? So look at its frequency domain representation. The signal XPB is having a triangular shape of spectrum in the frequency domain. and the output signal YPB is in the blue color, and the input signal is operating at a frequency of FC, the central frequency. It has a bandwidth of B. So within this band, the transmitted signal spectrum and the received signal spectrum, if you are looking at, the received signal spectrum is like come down from the transmitted signal spectrum, and also the shape of the signal spectrum is also distorted. Okay. So this is happening because of your impulse response of your LTA system. So the communication channels or maybe systems are actually the filters. So they create your X of X PB of T and Y PB of T. If you look at, so when X PB of T is the transmitted signal, it hits a building and comes to the receive antenna. If there is a direct path directly coming to the antenna, if it's a reflecting path is available, then it hits the car and coming to the antenna. That means the received signal is actually the summation of all the three signals are placed at this point, received by your antenna. So each path is having its own delay, that is T1, T2, T3, and each path is having its own gain, ρ1, that is a power actually. So we made it as root P1. So P1, P2, P3. Then the impulse response of the system, nothing but a delta function of with gain and the path delay. So delta of T minus T1, delta 2 of T minus T2, T minus T3. Sir, in between, if you have any doubts, you can stop me at any point of time, no problem. I can answer your questions or use your chat box so that I can answer immediately. So now look at the complex baseband representation of the signal. So in the communication theory is developed for the baseband. So from baseband, we have to pass it to the real passband. That means we are centered at FC. So these two frequency spectrums of your received signal, we have to remove your carrier frequency, then we have to start your signal processing, right? That means from FC we have to bring it to the zero frequency, centered at zero. Then this is called complex baseband signal. So this complex baseband signal from FC, it has come down to zero axis. So if you look at X of F and Y of F, and the bandwidth of this system is B by 2, whereas if it is in the real passband, the total bandwidth of the system is B, because we consider only the positive side of the frequency signals. So when you are downshifting your signal from real passband to the complex baseband, when you are moving the signal towards the zero axis, so we have to consider only positive frequencies. That means our bandwidth has become B by 2, right? So we can see the real passband signal XPB. So where it is placed at a frequency of FC. That means it is shifted to a value of X of F minus FC plus X conjugate of minus F minus FC by root 2. So we know very well the real signals. Similarly, output Y. Y is also given. Now X of T, Y of T. So that is a linear time invariant impulse response. We know X of U into X of T minus U du. So this downshifted channel. What is a downshifted channel? Is nothing but your H of T. So how this is H of T is different from the high frequency channel? So high frequency, that is when you are passing the signal through a real communication system, that means the signal is already multiplied with a carrier frequency, right? So when it is multiplied by a carrier frequency, the frequencies are near around your carrier frequency FC. So this downshift, when you do the downshift of your signals, it is nothing but multiplication with e power minus j 2 pi fct. That is called a baseband channel signal. For a passband, it becomes e power j 2 pi fct. Okay. So now we analyze this reconfigurable intelligent surface. So there is a transmitter and an RIS with n number of patch antennas are placed. All these n number of patch antennas are having a switch, independent switches, and every switch is controlled with a programmable unit. So then based on the switch operation, the RAS is reflecting the received signal to an intended direction. This is re-radiated signal. So this intended direction is going to the receiver. Okay. Now we need to understand here, if you place an RAS element on the top of the wall or upside of the wall, so from the transmitted signal, normal base station, when it transmits the signal, it hits the buildings, and then it all the scatterings, reflections, so all will come to your receiver. Now we have an additional radiated signal. We have an additional RAS element which is placed on for the side of the wall. Okay. Now we have to see that what is the end-to-end system with impulse response. So X PB of t is your input and Y PB of t is the output which is received at the receiver. So we have to imagine that from X PB of t to Y PB of t, there is one direct channel. So if there is a direct path, the signal goes directly to the receiver. So that is represented by HD PB of t. This is called direct channel. Then some other values. What are those values? So the signal hits to the patch. From the patch, it is redirected towards your towards your intelligent surface, right? So that means, please give me some time. Hello, Kalpana. So we have based on n number of elements, each element has some gain. So we represent that gain by A1. So signal goes to this patch antenna and it is multiplied by the gain and the path is decided by it. Then it reflects towards the antenna. That means when it is reaching to the element, there is a channel. From the element to the receiver, there is another channel, right? So there are two channels in between for each path, for each RAS element. When a signal passes through the RAS element, it is going through two different channels. One is from transmitted to the RAS element. Another one is from RAS element to the receiver. So we have placed n number of elements. That means the signal is passing through all, suppose, n number of elements. We take element 1 to element n, and each element is having a signal, and that element is when it reaches to the element, we are making the formulation of your signals. So this is the formulation V1 PB, and we are multiplying with the phase theta I, and then it takes then another channel, that is B1. Then after that, upon these multiplications, it comes to the receiver. So such that for all n number of elements, a signal is received to the receiver. Okay. So if you find solution for this signal, impulse response, there is a one direct path and rest of all indirect paths, impulse response of the system. So one is B, that means of at the receiver, the channel, and the another one is A, that is from transmitted to the receiver channel. And V, in between V, we are multiplying with the phase factors. Okay. So what to be controlled now? We have to control this RAS using the phase factors of the RAS elements. So we have to control by RAS using theta 1 to theta n, right? So this is the basic concept of the formulation of the received signal from a reconfigurable intelligent surface. So now, how will an RAS element filter the signal? So this is the one prototype taken from the internet, from the research paper. So this is a prototype for 5.8 gigahertz band. It has 55 columns and 20 rows, and RAS elements are placed at this. And example, a patch with the bias voltage V is applied, and it has a reflection coefficient. And it has a reference is taken from this paper, RAS aided wireless communication, prototyping, adaptive beamforming, and indoor-outdoor field trials. So this one, If you look at the frequency versus the phase response in degrees, more or less, if the frequency response is at 5.8 gigahertz band, the design patch antenna is for 5.8 gigahertz band. So exactly at those bands, we can see that the gain response of the system for different bias voltages from 0 to 19 volts, because each band antenna is connected with some bias voltage to make it on, right? So after consuming all this, it is showing the response of the system. Now, the second diagram, if we see, that means what is the patch? The patch is placed on a dielectric surface and it is made on and off through a switch. So exactly at 5.8 gigahertz, the amplitude response more or less for different values of biasing voltages, we are seeing the amplitude response of the system. Now, how to transmit the data? So we know the pulse amplitude modulation or binary phase shift keying, quadrature phase shift keying, any kind of waveform, we transmit a signal. Let us take one example. Suppose we are taking a pulse amplitude modulation scheme, then what we are transmitting, each amplitude is multiplied with a pulse, a shifted version of the pulse. That means x of m is your signal amplitude and it is multiplied with a pulse which is shifted to a value of m by bandwidth, right? So this is called a discrete sequence. X of m is your discrete sequence. That is nothing but your amplitudes of your signals. So use a pulse. PT is the standard pulse we use, and using the Nyquist criteria we know very well. P of m by b must be 0 for integer not equal to 0 and non-zero for m equal to 0. So we take one pulse, that is a sync pulse. So this sync pulse, when it is multiplied by the different amplitudes, so if you look at for a duration of Ts, we are transmitting the each pulse amplitude. So x0 is the first one is multiplied. Then we place another pulse, shifted version of the pulse with a multiplication factor of 2, that is the x2, and another pulse with a negative dimension, negative direction. So we placed another pulse because it's a sync pulse, right? So now because it is a discrete kind of a transmission, if you look at the pulses are added in this shape. So the sampling of the received signal, if you would like to compute, so this signal is nothing but we want to isolate x0, x1 and x2. So if you sample your output using your matched filter response, so at kth sample, if you see that this signal is nothing but your transmitted signal. So now we introduce a channel. So this is the previous one is fundamental principle of your transmission of signal without a channel model. Now if you place a channel model, that means x of t is convolved with h and we add omega of t. Omega of t is your additive white Gaussian noise. Now we are using a basic pulse, that is a sync pulse, root p sync bt. So what is received signal in convolution between these two? The pulse and the while. So that means x of m pulse is convolved with the channel and the gain. And again, so when it is coming to the patch antenna, again it will another channel. So it comes to this point. So when you sample the received signal, we are seeing the effective pulse function and a complex Gaussian noise is also added to this. So this is a scenario of your narrowband channel. So generally the narrowband channel we take it as a constant gain and it is a delayed version, that is delta of t minus t in the band. So if it is Nyquist criteria is satisfied, your Zk is constant multiplied by xk plus Gaussian noise. Okay. So putting the pieces together, so if direct path, signal and related to n element paths, these are the signals. So each path is having a gain and it is elevated to a value of e power j2 pi fct and the corresponding time delay. So now what is the final end-to-end discrete time system model? So final end-to-end discrete time system model, if you look at, there is a direct path signal and joint amplitude path loss. That means T of n into A. So the signal is transmitted from the transmitting antenna, hit to the RIS. So that delay, that is TNA, and T theta n, this is inside your RIS element. TNB, that means from RIS element to the receive antenna. Okay, so these are all delays are added to e power j 2 pi fc. So this is called a joint delay and is also tunable because tau theta n is in your control, multiplied by x of k plus noise, right? So this is the amplitude loss, alpha, beta and gamma, because from the transmitter it is received by the patch, received by RAS, and RAS has a gain of beta n, and from RAS it is received by your receiver. So we have another gain called gamma n. Alpha n, beta n, gamma n are their powers received. So we make square root of the powers multiplied by e power j 2 pi fct. But when the signal is transmitted, it is elevated to a frequency of fc. And because of these channels, we are connected with 3 different delays. So now, optimizing this narrowband communication performance. So what to do in this? So to maximize the performance, for time being, we ignore the direct path. So for maximizing the performance without the direct path, if you look at this system, alpha, beta, gamma, n, and the received signal without a direct path, signal and noise. So we have to apply a signal processing problem over here. So the maximize the signal to noise ratio, similar to your digital communications scheme. So that means this whole component is called signal component added by additive white Gaussian noise. So we have to maximize the signal component. So that means to maximize the signal component, take the absolute value of the signal. That means suppose if you are taking alpha, beta, gamma, n as simply alpha, beta, gamma, for all n it is common. Then, so this whole of alpha, beta, gamma, n will become a fixed one. So generally this whole square signal power, when you compute the power, I have to take modulus operation and square of it. According to Squart's inequality theorem, it is always less than or equivalent to, for n number of elements, alpha, beta, gamma, n square, because the e power j mod is 1, right? It is always less than or equivalent to this. So such how many elements are there? Each alpha, beta, gamma, n are only alpha, beta, gamma. So we are taking that one as alpha, beta, gamma only. So when you are making it square, n square times alpha, beta, gamma. Okay. So minimum positive delay such that theta of n we control this theta of n such that the delay solution between the maximum value of TMA minus TMB. So this is TNA minus TMB. So we take these two and then we subtract with TNA minus TNB. That we consider it as theta n. So because we have to somehow nullify the value of TNA and TNB with your T theta n. Okay, that is a principle to overcome the channel effect. So using this principle, we can construct RAS elements, and already mentioned about it. So this is the basic principle of RAS element, and it's also a very low cost, and it has some passive reflecting elements integrated on a planar surface, and when signal is coming to the surface. So how do we construct this planar surface? Using a meta surfaces with sub-wavelength atom size, and it enables us to manipulate the reflected angles. So with these basic fundamentals, now we'll move to the original work what we carried over at NIT Waranga, and presently what we are doing an experimentation as well. We have designed this RAS of our own. And now we are testing with our wireless communication testbed. So with the experience of wireless communication testbed, on top of it, we have added an RIS, and RIS is added to the system. And now we are working on that system. Okay. So now try to see that again, one more time I am revising. So working of an IRS system. So electromagnetic waves transmitted from the base station are impinged on your IRS. Then this produces an induction current into the IRS. Okay. So now this IRS reflect these signals towards the users. So during this reflection, actually the IRS changes the response by controlling the phase and amplitude, two elements. Phase and amplitude. So phase shifts are controlled by your pin diodes used in the IRS. So let's have a look at one IRS, how it is designed. So there is a copper backplane. So there is a copper black plane. On top of it, we have used a substrate. So these are all patch antennas are placed. These are called reflecting elements, are also called meta atoms. So each of which can independently impose the required phase shift on the incoming signal. Okay. So beyond this copper backplane, there is a control circuit board is there. That is IRS controller. So this using this IRS controller, and if you look at the pin diode, how it is connected using a DC feeding via hole. So pin diode and a tunable reflecting element. Okay, that means the switch on and switch off. So equivalent circuit of a pin diode. If it is switch on, it is acting as a resistance. If switch on, it is acting as a capacitance. So this reflecting coefficient of each element must be a tunable one to serve for to control the wireless channels arising from the user's mobility. So we need the reconcilability in real time. So these IRS elements actually acts as a gateway to communicate and coordinate with other network components through separate wireless links for low rate information exchange. So look at the outer layer. Look at the outer layer, middle layer, and the RIS element. So the RIS, the outer layer is actually a dielectric substrate with IRS elements. So these elements are directly interact with the incident signals. So these elements use pin diodes. So these pin diodes helps in controlling the phase response of your scattered wave. So we divide into inner layer, middle layer, and outer layer. Outer layer is our RIS element. So middle layer is your substrate. Inner layer, other side layer is used for the controlling, placing your control of your control unit. So and also this one supports up to 6 gigahertz. It supports we can design up to 6 gigahertz to terahertz, whatever the range you require. So we have designed for 5G communication. And look at the middle layer. It is actually a copper plate which prevents the signal leakage point. And the inner layer consists of actual control circuit board that is called IRS controller. So now the different phase shifts of IRS elements. Actually, we have designed through simulations, and also we have real time we made IRS element of our own. So using our CST software. So these IRS elements can be realized independently while setting the corresponding bias voltages of your pin diodes. Okay. So what is the advantage with these IRS elements? So as I said, those blocked subscribers are benefited because of IRS simple placement of the IRS element. Not even if there are minimal number of users are present in such areas, construction of a base station at those places is cost effective. So the 3CPP model says that IRS element will give a large benefit to the users. And also it offers better beamforming gain compared to the massive MIMO. And the received power is as the number of antenna elements are increased from your MIMO case, it also increased by a factor n square in IRS. So you see the difference between massive MIMO to IRS elements. There you have to place the n elements here using a factor of n square in IRS. But anyway, it is only a kind of a patch antenna construction. So it is very cost effective for wireless communication vendors. So, and also it extends network coverage or base station coverage by serving edge users or subscribers. Okay. As I said earlier, it is a passive reflecting elements. So it does not require any ADC, DAC and amplifier devices. Generally we use in classical relays. So that means reconfigurable intelligent surfaces are available at affordable cost, easy to implement and flexible to deploy, and also we can extend in several places. And this IRS integrates a large number of antenna elements in very limited compact space. But some disadvantages is it does not outperform the relay. So relay is a real communication system, right? But whereas RAS is only a small patch antenna placed on top of the walls or on the buildings or on top of the trees. So to extend your range. So if you want to make the performance similar to relay, we require a meta surface with higher number of elements, approximately 200 elements if you can place. Maybe we can replace your relay. So these IRS elements do not support any digital processing capability, but as it is designed based on concept of analog beamforming. So there is another disadvantage of IRS elements. And the channel model. So anyway, I already told the channel model for a discrete time model, the baseband equivalent model at IRS element. So beta, e power j theta n and x of n. So this is the reflection amplitude, phase shift and number of IRS elements. So if beta equal to 0, then it is absorption. If beta equal to 1, it is a full reflection. So how you design your antenna, you want to use it as a reflective element, or you want to use it as an absorption element, or you want to use it as a omnidirectional transmission, right? So if you use the beta as 0, it makes absorption. If you use beta equal to 1, fully it reflects from the surface. So this beta is always between 0 to 1, and theta of the phase shift control is 0 to 2 pi, and we use n number of IRS elements. So now again, I don't repeat the same baseband model in the different scenarios. So the baseband equivalent channel model for a narrowband system I already explained earlier. So here also again, if you use H, G and beta n concepts. So if you take a single antenna element n, it has a gain y from the antenna element when it reaches to the end user. When it reaches to the X user, it is taking a different distance and channel gain and antenna elements. Okay, so with this, I'll go to the I'll go to the original work, what is carried over at NIT Warangal. Sir, how much time is left?
Around 10 to 15 minutes, madam.
Only 10 to 15 minutes.
Maximum 6:45 minutes.
Okay. Then, okay. So then I just give a glimpse of what the work we have carried over. Okay?
Yes, madam.
On RAS for 6G communication systems. So quickly I go through the slides.
Okay.
So we did IRS for CISO analysis and the Nakagami M fading channel. and multi-antenna, multi-IRS assisted system over generalized K-mu fading channel, and multi-antenna, multi-IRS assisted system over generalized N-mu fading channel. So first we formulated and multi-antenna, multi-IRS system or generalized alpha mu fading channel. The channels, different channels we have used, and also UAV communication, IRS mounted UAV communication is also explored. As we know, the data is increasing. We need the, because of the data crunch, and also the users are exponentially increasing. We need to place many number of base stations in different places. When there is a huge traffic, definitely we have to place a base station, but the traffic is less. But when the signal is not reaching to those areas, the better option is only IRS. So this IRS compared to massive MIMO techniques, as I said, so massive MIMO fails to solve the blockage problem, but IRS with the signal direction, integrated signal direction, it reaches to the every signal. Okay. So now look at the 6G enablers. So protocol level, infrastructure level, and spectrum level. We came to know that millimeter wave to terahertz communication, ultra broadband systems, optical wireless communication. In protocol level, we do in channel coding, machine learning aided algorithms, fully coverage broadband connectivity. And infrastructure level, ultra massive MIMO. Another area is intelligent reflecting surface and integrated space and terrestrial vectors is the present day trend in wireless communications. So we know the basic principles of wireless propagation environment. So now coming to this IRS reflecting element, as I mentioned earlier. So the reflecting signal by an nth element of the IRS denoted by yn, then it's given by multiplying the corresponding incident signal denoted by xn and with a complex reflection coefficient that is e power j theta n. So xn is the received signal, bn is the gain of the reflecting element, and it's the phase angle of this theta n, e power theta n for n number of elements, where beta n, I said already, it lies between 0 to 1, because if you want to fully use it as a reflecting element, we have to fix beta n as 1. And theta n, the phase angle to which angle it has to reflect, it lies between 0 to 2 pi. So with this system model, IRS reflecting element, so we are going to the I already narrated the advantages of IRS system. Then, so some of the research gaps we found. So most of the works, when we gone through it in single, double, they have used a fading channel model between 1 minute. The fading channel model from the transmitter to the IRS element, and from the IRS element to the receiver, there is a wireless channel. So they have used the general fading channel models, the relay fading channel model in the literature. So IRS is anyway, it's a low cost, flexible, and it creates a virtual line of sight between transmitter and receiver. And it does not need any ADC, DACs, and power amplifiers. So with this introduction, so we found some research gaps. So mostly they use single or double relay fading. Double means from transmitter to the receiver one channel, that is a relay fading, one relay fading, and IRS to the receiver is another relay fading. That is called a double relay fading, IID channels with the line of sight case, and they have derived some closed form expressions for bit error rate. And some of the works are focused on spatially correlated channels. So that means the transmitted channel and from IRS to the receiver channel, they have some correlation coefficient with the relay fading channel and provided some closed form expressions. So with this mathematical background, and because our earlier research work is on derivation of the closed form expressions for ultra wideband communication. So we used the same mathematical models over here, and the fading channels are changed. So that how the system model is coming down to exact expressions. So we have used in this, we have used a double fading with the non-line of sight channel. non-line of sight system. And we have used a multiple IRS wireless networks, and we are also used spatially correlated channels. So the another work is carried over on IRS mounted UAV communication. And now currently we are doing real-time communication test bed. So we focused on these 3 areas, 1, 2, 3, 4. The current work is in real-time model. So with these objectives, so the first IRS assisted some CISO system is computed. So what we did, we find the exact bit error rate and expression under Nakagami M and log normal fading channels in non-line of sight scenarios is derived using a moment generating function approach and compared it with the simulation results. So to go thoroughly through this base mathematics, it takes long time. So what I can show that, so we have considered H1 is one channel, G1 is another channel, right? So, and also from the base station to the IRS element, like that, N reconfigurable controllable elements are there. So N independent reflecting coefficients. The received complex gain is computed. First, we formulated a channel model, and we have considered the channel envelope follows an independent and identically Nakagami distribution with the following PDF. That is, we know very well the Nakagami PDF, where these values of M is defined as the fading severity, and omega gamma is ohm is average power. So with this PDF, Nakagami M PDF, if you look at the Nakagami M PDF in a closer distribution channel model, with the signal amplitude is increasing, the probability density function of your Nakagami fading for various M values of Nakagami. So that is called M equal to 0.5 is called one-sided Gaussian curve. When M equal to 1, it becomes a Rayleigh. So this is my Rayleigh fading channel model. And M equal to 2, it is called a mild fading. And M equal to 5, it is almost near to your AWGN channel, right? The Gaussian model. So I'm just skipping the mathematics, what is proposed. So we computed the received signal at the destination, and we computed the received SNR, signal to noise ratio, at for the D user using these what I said earlier. And to maximize this SNR, the optimal choice of theta. What I said in RAS elements, we can control theta of n, that is incident angle and reflection angle, right? So signal is incident on IRS and signal is to be reflected from the IRS. That is called the optimal choice of V of n is equal to phi of n plus psi of n. So to maximize this instantaneous SNR, the formulated the equation, and according to the central limit theorem, when n goes to a large value, so the Gaussian random variables with the following statistics, a non-central chi-square distribution with 1 degree of freedom using a moment generating function, we express the signal and using the math. So we have computed the average probability of error for an MPSK signaling scheme using the probability of error. We need some mathematics to derive these equations. Okay. And for M equal to 2, that is a BPSK case. So the probability of error is derived in a closed form solution. So these are the closed form solutions. Sir, should I stop?
Close, madam.
No problem.
Another within, maybe I'll just quickly go through my works. I'll just show the quickly what we have done. So without explaining much of the mathematics. Okay?
Yes, madam.
That will be maybe there. Some of the participants, if they are working towards IRS, it will be helpful for them.
Okay, madam.
So these are the results what we obtained for BR performance for RAS scheme with N elements are 32 we have used for BPSK signaling for using the fading severity. So what we understand, so blue line is theoretical, that is what we derived using mathematics, and other lines are simulations. So closely approximate matches happen. And also BR performance of IRS scheme for varying the number of reflecting elements. So if you increase the number of reflecting elements to a large value of n equal to 32 with a severity of fading m equal to 2 with a BPSK scheme is mentioned over here. This is one of the work what we presented, right? So the another work is IRS aided indoor communication channel model. So here we have assumed the reflection coefficients are having a phase element and a gain factor. And the channel model is slightly different from the previous channel model. Here we have used a log normal fading distribution. Earlier we have used a Nakagami fading distribution. So for this log normal fading distribution, we have calculated the bit error rate probability of our, first we maximized the signal to noise ratio. From the signal to noise ratio, we found the probability of error calculation using moment generating functions and hyperbolic geometric functions. So these are some of the results where we can see the performance by varying the number of reflecting elements. This is totally full of mathematics, right? Without explaining on the board, I think we'll go to, otherwise you have to read the papers of our lab. So using IRS elements, the performance of the BER is achieved by 3 dB gain, employing more number of antenna elements. Okay, so that is our one. So we can see some of our publications from Suresh and me and my previous student. So he has published into Indicon journal, Indicon conference. This is the very beginning. So impact of Nakagami M fading channel and on reconfigurable intelligent surface symbol error rate in non-line of sight scenarios is the one paper. Another one is on using a log normal fading channel is another paper we have submitted for both the for different years of Indicon conference. And now we extend it to multi-antenna, multi-IRS. Antennas are also, that means the transmit antenna and receiving antennas are also MIMO case. And we deployed an IRS assisted system over generalized fading channels. So for this, so like this, you can see L number of antennas are placed in the base station and IRS elements. So we placed multi-IRS elements, one of IRS1, IRS2 and IRS3. Then there is an obstacle between the transmitting end and the receiving end. So for this model, we compose the mathematical formula. And finally, we have derived. So here we have used a PDF K-mu distribution. So each time we have changed the distribution model as well. So using the K-mu distribution, the final probability of error is computed using moment generating functions and hypergeometric functions using the central limit theorem. So these are the different values are placed. So we have achieved a better BER performance, and also the simulations and theoretical match is happening. So increasing the K value directly indicates the improvement in the power of the dominant waves, and thus the BER is decreasing. So this is another work. That means multi-antenna and multi-IRS system. So this is another area where we have focused. And so the another one is K-mu fading channel, already mentioned, multi-IRS, multi-aided communication channel model. So you can see the look at the model, multi-carrier simulation setup. Then we have used another distribution. Chi-square distribution is used. For the chi-square distribution, what is the probability of error is computed. So if you know the fundamentals, we can go to the real communication. So here we made 4 contributions in wireless personal communication and IEEE Latin America transactions, and few more papers are under review. So then we have also computed error rate analysis of IRS aided system. It's spatially correlated some correlation is also added to the generalized fading channel models. So with this, so we have formulated the equations and finally computed signal to noise ratio and probability of error computed. So finally, we have used this IRS is mounted on a UAV. So what is your RF energy harvesting is also explored. So that means you look at you have RAS is mounted on UAV. So and UAV is moving, right? So the power station is transmitting a signal through a channel H0, and UAV is placed at the top of the building. From UAV, the signal is received and it's a two-way communication. So we have formulated the models for UAV communication. And finally, we have designed the signal model. So with this, we got a Springer, and so some of the publications also we filed patents.
Unknown caller.
Some of the works are under review. Some of the references we can go through, and you can see our just a minute. So if you have any questions, floor is open.
Audience, any queries you can ask.
Madam,
Sir.
this IRS is completely different from FSS, na? Frequency selective surfaces.
Yes, sir. Because our reflective coefficient is 1.
Okay.
We make for this IRS, and also this element is connected with a switch and a control unit.
Though it is a passive.
Though it is a passive.
Okay.
It's a passive, but we have a control of this passive element.
But will there be any interference between the incident waves and reflected waves?
Yes, sir. That is the one work is mentioned over here, no?
Okay.
The correlation coefficient.
Correlation coefficient. Okay.
So we worked on the correlation coefficient as well.
It should be completely different.
It should be completely different.
Okay.
And it's only we contributed to the mathematical work. And this year also we are working on the real model, because we have already constructed a test bed, right?
Okay.
We have constructed a test bed. So on top of the test bed, we are 1 minute, sir. I can show you my papers. Okay. So these are the new papers, performance analysis of and also one important information to all the faculty members and in this workshop. So we can add your Google Chrome on top of your publications. It will show you whether it is comes under Q1 journal, Q2 journal, can be easily viewed on your Google Scholar citation.
Okay.
So these are the papers on IRS system. So in 2025 papers, all 2025 papers are IRS. Now we are physical model is also ready. So, but the work is not disclosed. It is under writing.
Madam, after getting reflected, if the polarization is also changed, there might be a less interference, na? That is also one method.
Yes, sir. Yes, correct.
But you are actually working on to what do you call that correlation coefficient? It should be 0. Am I correct, madam?
Yes, sir. First, initially we took correlation coefficient as 0. Later, we introduced some correlation is there.
Definitely, it will be there. Okay.
Different, it will be there.
Though you are using active devices, but you are calling it as a passive reflector.
Passive reflector, because it's a minimal power, only for control unit and to make the switch on and off.
Okay. you can use meta surfaces also to increase the gain.
Yes. Meta surface also, yes. I'm not antenna expert.
But
I'm a
anyhow,
communication expert, but we have done a physical model.
yes, okay.
Mhm. So antennas experts, they only design an antenna.
Yes,
And
yes.
and also they don't implant their antenna to a real-time communication. But what we are trying to see that even though we doesn't have any much knowledge about the antenna system design, we designed this patch and with the pin diodes and the control unit also designed by our own students. Now we have used 2 horn antennas for the transmission and reception. In between, we placed IRS element. And by changing the direction of these horn antennas, whether my IRS is able to do the reception properly or not, because the IRS element is controlled by my control device, right?
Oh,
So
yes.
I programmed the control device in such a way that if my received signal coming to the RIS, to the what direction it has to reach, that is controlled by through program.
Okay.
So that way we have designed it.
Madam, do you have that chamber with you to measure the gain or radiation pattern in the
No,
NIT?
we don't need any chamber like your antenna people do the measurements in anechoic chamber, no sir.
But you don't do it.
We don't do it. We do it in the open air because for us communication is important.
Okay. So you will come out from the chamber.
Yes, we never use chamber.
Okay.
Excuse me, ma'am.
Yeah.
Ma'am,
tell me.
how this RIS is you have interfaced with programmable controller. So if it is discretized, then you could have used this Poisson's distribution, right? In your lecture, you said about this Gaussian, right?
Yeah.
Why, ma'am?
नहीं लेकिन मैंने आरिफ भाई से बात की हमने बोला नहीं कि आपको अरे यार मैंने किया ना उनको खुद होके आज मैंने फोन किया
Can you repeat your question, madam, one more time?
ठीक है yes,
Actually, this RIS is directly interfaced with programmable controller, right? So
Yes,
you are discretizing the values. So if it is done,
no, we
why
are not
did you go?
we are not discretizing we are not discretizing the signal.
Okay.
Only RIS element, whether to make it on or off.
yes.
Suppose there is a 60, let's take 4x4 elements.
Yes, ma'am.
Each row we have 4 elements. So to make towards the desired direction, maybe I am making on 2 elements of diagonally. So I don't have any discretization over there.
So here reconfigurable in the sense like
reconfigurable in the sense I am controlling which patch must be active.
Okay, ma'am. That is through programmable controller.
That is through programmable controller.
Okay, ma'am. Okay,
that is only the concept behind it.
Okay. Thank you very much, ma'am.
You are from?
I'm from VJIT, ma'am.
Okay. So if any faculty are interested to do their research, if they want to do for PhD program with NIT Waranga, you are most welcome. And part-time, full-time, both possibilities are there. Without GATE also now we are taking for full-time PhD. And with a stipend of 38,000 for first 2 years, 41,000 for rest 3 years with HRA. Sir, are there any other doubts?
Thank you, madam.
Thank you, sir.
So participants, please wait for validation condition. We will complete. So after validation, we will conduct exams. I will share the link also.
Sir, I'm leaving the meeting, okay?
Yeah, you can leave, madam. You can leave.
Okay.
Thank you, Mani madam.
Kalyani madam.
Thank you, sir. Thank you for inviting me to this program.
Excellent talk, madam.
Thank you so much, ma'am.
Yeah.
Kalyani madam.
Sulakshana, madam, Mani madam, Sulakshana.
Oh,
Ma'am, I'm
Sulakshana.
Sulakshana, ma'am. Yes,
Yeah,
ma'am.
Sulakshana, you are also there in VJIT.
No, ma'am. I am the participant.
Oh, okay.
Great lecture, ma'am.
Thank you so much.
Thank
Okay,
you,
bye,
ma'am.
madam.
Yeah, thank you, sir. I'm leaving the session, sir.
हेलो हाँ सर बरोबर है लेकिन अगर उसके अंदर और भी जो फर्स्ट पैराग्राफ है ना उसमें लिखा है ना आपने कि आई एम द ओनर ऑफ द ये तो उसको ओनर और ऑब्लिक में डेवलपर लिखने का
Good well.
Hello, sir.
Those who are present now, you give them as attended.
Adhe, sir. Adhe, after valedictory, we can start now, sir. We will start valedictory now itself.
Okay, but okay, sorry.
After that, they will not join or not. No, that I will take care, sir. That certificate I will
Okay,
take care.
let us finish off the valedictory. Then you tell the present. You tell the first.
Yeah. That I will take care. Participant, don't worry. I will take care of that certificate. Okay.
Participant, please mute yourself. Please.
Participants.
Have fully rights to sell the set shop number 1 to any other person. There are no spending to be paid to be. उसमें मेरे को और कुछ पैसे देने के नहीं है सर. Mr. Arif and Mr. Arif are willing to purchase the set shop number 1 for which my consent is necessary by selector. I'm giving you the no objection for transfer of shop number 1 on purchaser's name, and also I will be present for document registration as consulting party.
Hello, sir. Hello, sir. Sir, wait for some time, sir. We will do it. Okay.
Want to mention the rate on PNC tax receipt and NSCB liability. यहाँ पे सर उसको रेफर किया.
Hello.
After getting official certificate of the building, the name of Mrs. and Mr. Arif will come on the share certificate and also on completion certificate.
Hello, sir. Hello. Kaleni madam. Hello. Hello, madam.
Good evening, all. Let's